Log on, tune in, find out. Another good idea from Cambridge.
And she's going to be talking about optimal designs for pharmacokinetic and viral dynamic nonlinear mixed effects models.
Thank you. First, I would like really to thank Sergei and Barbara for organizing this workshop. I think it's very successful and I'm very pleased to be here. Second, I want to say that I've changed the title of my talk when I submitted the abstract, but the abstract was put on, but not the change in title. But it's also about drug exposure and response. And third, that this work is a joint work with Caroline Basoli, who was a former PhD student who now has a position as an assistant professor in Grenoble University in France. So I think I will start by the definition of pharmacometrics, which is called as the science of quantitative clinical pharmacology. And indeed, the idea is to use all data generated during clinical trials and patient care and to extract as much knowledge as we can in order to have either rational drug development or, if you're a physician, an optimal pharmacotherapy. And the work of pharmacometricians is indeed to do this analysis, but it's also to use the results of this analysis to design next studies, and this is what we're going to do here. Clinical pharmacology is a science where you study the link between I knew I was going to make a mistake. No, that's also a mistake. And then where's the pointer?
It's near the top.
It's near the top. Oh, I found it. Sorry. And so pharmacokinetics, we've heard examples yesterday, is the relationship between dose and concentration, mainly in plasma. Pharmacodynamics is a relationship between concentration, mainly in plasma, and pharmacological effect or biomarker. And then, of course, you have now what we call disease models, and we've seen an example. These models or these techniques are applied both during drug development but also in clinical care. And the main statistical tool to analyze this data, which are mainly continuous measurements, not only but mainly continuous measurements, are nonlinear mixed effects models. Oh, okay. So my focus on my talk will be the design of studies in nonlinear mixed effect models, because now there are several methods and software that do maximum likelihood estimation using these nonlinear mixed effect models, and I'm not going to discuss about all the approximations and methods. I'm focusing on the problem beforehand, which is the choice of what we call a population design. It's a population design because we have several individuals, and each individual will have several sampling times. It's mainly longitudinal models, concentration time profiles, effect time profiles, and how many patients, how many sampling times, what is the base balance, and where to put the sampling times. And because these techniques are more and more used in drug companies, this is an increasingly important task. And it's very difficult when you have complex models defined by ODE to try to guess what are the good designs or the good empirical designs. And as we all know here, it is very important to choose good designs because it will influence precision of estimates, but also power of test. If you have very poor design for complex models, you can have unreliable studies where you will not be able to estimate all parameters. And in special population, like for instance in pediatrics or in old patients, there are sometimes limitations on the number of samples that could be taken. So you have to go to sparse design and you have to use nonlinear mixed effect models. And then it's even harder to find the good sampling times because each samples have a lot of information. And indeed, in the guidelines for population pharmacokinetics analysis, both of FDA and EMEA, there is a specific section about design consideration and that design should be studied. So the example I'm going to use are examples of data taken from this trial. This is a trial sponsored by the French Agency on AIDS. ANRS is a French agency on AIDS. The primary objective has nothing to do with what we're going to do here, and we published the paper. I'm more going to explain to you what the trial was. We had 115 HIV patients starting an active treatment, and by active treatment, it's a combination of three treatments. They received 2 reserve transcriptase inhibitors, which I will call RTI later on, and one protease inhibitor. We had measurements both of concentration after 2 weeks of treatment of all the drugs, but also of viral load, which is, we want it to be as small as possible, and CD4 count during 1 year of follow-up. So my talk will be about first developing a PK model of one of these drugs, not all of them, so AZT, and its intracellular metabolite. To develop an HIV dynamic model jointly for both viral load and CD4, and to do optimal design for future experiments, although it would be separate. It would be an optimal design for PK and an optimal design for HIV, because they are very different time scale. This is a time scale of a day, and this is a time scale of a year. So the outline will be first to briefly summarize the work we have already done on population Fisher information matrix. Then I will show you the model and the optimal design to study pharmacokinetics of IZT and its intracellular metabolite. Then I will show the model and the optimal design that we use for HIV dynamic model, and then a conclusion. So, first some notation. So, for basic mixed effect models, that is a model with only one continuous response, I will use this notation. I have a vector y high of ni observations in patient I. F will be my nonlinear function. Psi high will be the individual design performed in that patient, so it's the sampling times Tij. Ti are the individual parameters for that patient of size p, and epsilon is a Gaussian zero mean random error. And I will work here with heteroscedastic error models, and I was surprised yesterday that almost all the talks assume constant errors, where here I will assume a combined error model where you can have additive error, but you can have proportional error or combined error. I assume that the individual parameters are random, so that there is decomposed, a part will be a fixed effect mu plus a random effect bi, which will be normal with mean 0 and variance covariance matrix omega. And that, as usual in pharmacometrics, you can have additive random effects, but also exponential random effects, so that all parameters here who have physical meanings, physiological meanings, will be positive. You just take the log and it will be the same thing. And here I will assume that omega is diagonal. So the parameters you want to estimate, which I'll call the population parameters or hyperparameters, are capital F size. The size is capital P. It's composed of all the fixed effects, the means, if you want, the unknowns in omega. For here, it will be the variance of the random effect, and the parameters in the error model. What's a population design? Well, a population design is composed of capital N individuals I's, and in each individual I will have one elementary design, which is the number of samples Ni and the sampling times. This elementary design can differ between individuals. They don't have to be exactly the same. And this individual design may be sparse, meaning that you cannot fit one curve if you only had one patient. The population design, capital Psi, is a set of all the elementary design, and the total number of observations is, of course, the sum of observation in each patient. Often, at the design stage, we will not design one elementary design per patient, but we will assume that we have few elementary designs, so there are q groups of nq individuals, and all the individuals in the same group will have the same sampling times, and we have to define how many groups, how many individual per groups, and the design. And often, and almost always in drug company, what they like is to have only one elementary design to be performed in all patients, because that's easiest, and then you have balanced design and everything. Okay, how can we do population design, evaluation, and optimization? First, we have to have some assumptions. So here I will assume that the statistical model, meaning F, random effect, and so on, is known, and that we have a priori values of the parameters. So here I will do only local planification. You've seen example of pseudo-Bayesian planification or robust planification. We want to evaluate and compare design, so we want to predict the standard errors that we will have for each population parameter, and or predict the power of the test if there are covariates in the models. We want also to find optimal design, and to find an optimal design you have to give cost, maximal cost, otherwise you'll go to infinity number of patients and number of samples, experimental constraints, and for that you want to get the smallest standard errors or greatest information of the data, or the number of stages needed for a given power. There are two approaches in pharmacometrics. One approach is to use simulation study, clinical trial simulation, which is often done, but as you know, it's very cumbersome and you cannot explore a lot of design, or use mathematical derivation of the Fisher information matrix. And as we are in Cambridge, I thought I will show this plot, this graph. I was surprised that no one else did it before. I found that in a paper in anesthesia. I don't know why it's a paper about ANOVA in anesthesia. And here in Cambridge, there is in the Caius College a stained glass about Fisher and Latin square. So, Basia, I hope we're going to visit that Thursday afternoon. If not, you don't know? We're not going to visit Caius College?
This college we wanted to include because of these windows.
Okay.
But they have another event at this time. So hopefully privately one can go at another time.
Okay. Because perhaps you know that Fisher was indeed working in Cambridge at the end of his life, and he was president of Caius College from 57 to 59. So there is stained windows about Fisher there. And there is a sentence I like very much from Fisher, is to consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of. So I think we all agree about that because we are in this room, but I thought I will share this view with you. Okay, so we use the Fisher information matrix and the Fisher information matrix for population design. It can be easily shown that it will be the sum of all the individual contributions. The Fisher information matrix for one elementary design is given by this usual formula. However, here we're dealing with nonlinear structural models so that we have no analytical expression for the likelihood. So if you have no analytical expression for the likelihood, you don't have any analytical expression for the Fisher matrix. So what we did quite a while ago is to assume that we could use a first order expansion of the model about the random effect given at zero, which is called in pharmacometrics the FO approximation, which is called in this field the MQL approximation or marginal quasi-likelihood approximation. And if you do that plus some other assumption that the variance are independent of fixed effect, you can derive analytical expression for this Fisher information matrix, which is composed of two blocks, one block for the fixed effect and one block for all the random components. I have to say that we have lots of debate about these approximations, and on Friday there is at least 3 talks about what are the best approximations to do in nonlinear mixed effect models. But I used here the simplest one. And in those papers, and since that, we have extended this Fisher information matrix for more complex models. Models with more than one continuous response, so multiple responses. Models where in addition to interpatient variability, you have intrapatient variability, for instance, several occasion crossover trials, and covariates. And I'm sorry here, I've quoted only the work performed in my team, although there are several groups in the world now working on that, and they're more or less all here. Steve Dufour from Otago University, Kay Ogenborough from Manchester University, and Sebastian that you've seen before from Uppsala University, and Sergei, I forgot, from GSK. Okay, so in all this work, we've performed extensive simulation showing that this approximation was quite correct. That's why I'm going to use this approximation. We also developed a software that we call PFIM for Population Fisher Information Matrix that implemented this previous approximation. It was developed initially by Sylvie Retou, a PhD student, and myself, and now it's been extended by other participants, including Tutu Nguyen, who is here. And it's using R, so it's a free software that you can download from here. The first release was 10 years ago, getting old. And we had a new release last year where you have this multiple response model with ODE, powers, discrete covariates, and so on. How do we perform design optimization, where we're using the de-optimality criteria, and you can use either optimize exact design or continuous design. For exact design, we assume that the design structure, so it is how many groups, how many patients, how many samples are fixed, and we try to find only the best sampling times. And here I'm going to use only this approach we're using continuous design or statistical design approach, where we optimize the proportion of patients on each group using a Federer-Wien algorithm, and Valerie is here, and I think Wien is not here, but he's upstairs, so I'm very proud of to be here. And where we can estimate both what are the best sampling times, but also how many groups of patients do you need, what is the best balance between the number of samples per patient and the number of patients. And the limitation, or perhaps it's not a limitation, is that in that case you have, or we have, to define a discrete set of sampling times and you optimize among them. So let's apply that to my two examples. First, pharmacokinetics of this drug, AZT, and its intracellular metabolite. So AZT was the first drug that was developed for HIV, and it's a reverse transcriptase inhibitor, and it's still used and recommended by World Health Organization for treatment of HIV infection worldwide. This drug is not active in itself. It has to be incorporated in the cell and transformed in AZTTP, and only this AZTTP is the active part of the drug. So this is very important to know. However, to measure the concentration of this drug, it's very costly and complex because it's intracellular concentration, much more complex than plasma concentration of AZT. So you have to do it in several specific laboratories, and you need specific additional samples than the plasma samples. We were lucky that because in this trial, we were able to have 73 patients receiving this drug twice daily, so that tau, which is the interval between two doses, 12 hours. And we had measurements of AZT in plasma at 4 different times after drug administration. But we also had AZTTP intracellular concentration measured. In 11 patients, we had 4 samples per patient, but in most patients, we had only 2 samples. We derived a joint PK model for both plasma concentration of AZT and intracellular concentration of AZTTP. I don't want you to read this equation, okay? If you want, there is a paper. It's just to say you that we assume that AZT is transformed in AZTTP. And because of no concentration or no measurement in urine, we can estimate 3 parameters for AZT, 2 parameters for AZTTP. And we did the analysis of the data with the SAEM algorithm in Monolix 2.4. Here are the observed data. So here is AZT, this is time post-dose, this is the concentration, and the red dots are all the concentration which are below limit of quantification, which were taken into account in our analysis. And here are the intracellular concentration with lots of variability. Here are the estimated fixed effects with quite small relative standard error. And here are the 3 random effects that we had in this model. And here are the error, which was assumed to be additive for AZT and proportional for AZTTP. Yes?
This is oral administration?
Yes, I forgot. Oral administration every 12 hours. But absorption of AZT is very, very fast. Yes. And perhaps you can see that indeed for Ka, we had to fix the estimation of Ka because we could not estimate it. You've been working on this drug. So, and here is what we call in our pharmacometric a visual predictive check, but it's explaining more what is the median prediction of AZT or the prediction for population parameters. And this is a 90% prediction interval showing variability. So we see a lot of variability here. What's interesting is to estimate the half-life. We see that this drug is very quickly eliminated from plasma, but yet we give it every 12 hours. Why? Because intracellularly, the half-life is much longer. So indeed, it's enough to give it every 12 hours. Okay, let's go for design. So we wanted to find an optimal design for that model. So we used the previous joint model, the previous estimated parameters. And first, we wanted to evaluate how good would be a design with 50 patients, 4 sampling times, but in each case, we will have both AZT and AZTTP. Then we want to do some design optimization, assuming a total cost of 400. Why 400? Because we have 5 patients, times 4 something times 2 drugs, which go to 400. We gave an available set of sampling times, and we use as a cost function the number of samples. And we try to derive what are the optimal sampling times if you assume that indeed we have the same sampling time for the two compounds, which is perhaps not very clever because they have very different dynamic process, or what is the optimal design if you allow for different sampling times for the first drug and the second drug. To do that, we use p-film, and it's just to show you that indeed we had to implement the model because it's not a model of the library of p-film, so this is the way you implement the model in R. And here is where you specify how many true responses, the parameters, the fixed effect values, the omega, the error model, and what kind of design you're going to evaluate. This is a part of the output, so for each parameter you get its value, the predicted standard error, the predicted relative standard error, and in addition to that you have the predicted Fisher matrix, its determinant, and so on. You get also a graph where here are the mean curves and here are the designs that you are evaluating. And here are some of the results. So here is the initial design with 50 subjects, 200 measurements for SZT, SZTTP, and its criterion. What's interesting is that the optimal design with identical sampling size, you've moved this last sample 6 hours to 0.5, and but it's even more interesting to see that if you allow different sampling times, you have early sampling time for SZT, late sampling time for SZTTP, only 3 samples here, only 2 samples here, and only one group. I didn't impose a constraint of one group of patients, but the best design is one group of patients. And you can see here that you need, if you want the same total number of samples, you need more patients, but you have a great increase of efficiency. But even if you allowed only 50 patients, you have an increase of efficiency. When you look here at the predicted standard errors for the initial design and these two optimal designs, you see they're doing a much better job for getting Ka and even better job for the other fixed effects. So that the optimal designs are better than the initial design, and allowing different sampling times for SZT and ZTTP, you have a better design and less samples in each patient, and especially your costly samples.
Are you particularly interested in KA?
No. I agree with you. I agree with you. I think, yes, I agree with you. I am not particularly interested in KA. I think what's important here, it's more this second example, where you see that you can, by assuming that you don't measure at the same time the two, you'll find different optimal sampling times. I agree that the part on K is not that important. And these are the optimal sampling times where you see indeed they're on different scales. What we did after, we wanted to use more complex cost function, because here I have assumed that the construction of the penalty was exactly the number of sampling times, the number of sampling times for SZT and SZTTP. As I've said before, intra-concentration measurement is much more expensive and should be done in a separate sample. So I assumed that it was 10 times more costly than this one. And I want to find what would be the optimal design if I assume this penalty. Or some people would say, clinicians say, oh, but the sample is not very important. What's important is a new patient in the trial, because a patient costs a lot of money, you have to screen it, and. So let's assume that each new patient has a cost, and I assume a cost of 8, which is the number of sampling times, and these are arbitrary, and of course you can change. And what will be the optimal design assuming this cost function? To do that, we had to extend the way we implemented the Federer-Film algorithm, saying that indeed the total cost will be the number of patients times here, and so that the Fisher information matrix can be written here as function of alpha q, but instead of alpha q and n, you can incorporate c tot and wq, and wq is a proportion of the total cost that you give to that elementary design. So we could use the Federer-Film algorithm, and the idea, of course, of using cost function is not ours. It was also by Sergi and Gagnon here in that paper. And indeed, you can find what are the optimal proportion elementary design, and then what are the optimal proportion of subject. And here are the results that we had. That indeed, we have very much different design now. We have design with several groups of subjects, so not all have the same design. And when you look here at the design for where you put a penalty for intracellular concentration, most patients have only one concentration intracellular, except 30% with 2, and much less measurement of AZTTP. And when you put the cost for each patient, you have much less number of subjects and much more measurement within each patient. So you can then play around with that. So we see that the design optimal reflects the imposed penalty. However, it's very difficult to compare the efficiency of these three designs because they have different costs and different cost functions. So this is a limitation. Okay. I move now to the third part of my talk, which is the model and the optimal design for HIV dynamic model. I'm going to use the results of the paper that we published early in this year in Biometrics, where indeed we performed a joint modeling of viral load and CD4 dynamics in this same trial. I have to say that in this trial, in addition to receiving different RTI or reverse transcriptase inhibitors, patients receive different protease inhibitors. Some receive lopinavir, which is still used. Some receive indinavir, which is more or less no longer used, and some receive nelfinavir, which is out of the market. And here are the data set that we got. Here it's log 10 viral load versus times in days, so it's 1 year follow-up for patients treated by lopinavir. And here is CD4 count versus time for patients treated by lopinavir. So you see here the data. So viral load hopefully under treatment decrease, and CD4 count hopefully under treatment increase. This is what we want. This is for indinavir and this is for nelfinavir. And perhaps you see here that in nelfinavir the response in viral load is less than in these two groups, and the increase in CD4 is less. I have to say also that we have a lot of data below quantification limit that was taken into account in the estimation. How to analyze this kind of data? You could first do empirical modeling. You say, let's say, well, this is like a linear curve and this is like two linear slopes. But this is not what we've done. We want to use more mechanistic modeling. And mechanistic modeling in biology, you use a mathematical representation of the biological system. So we're doing some simplification of the process, but we're using what we know about the biology. And so we're using dynamic models, which are often written as differential equations. And for instance, for dynamic of HIV and HCV after treatment, there have been papers quite a while ago in Science, in 1996 and 1998, explaining the differential equation to understand the action of this drug. And we wanted to use those models. I have to say that, for instance, this paper is the most quoted paper in PubMed about mathematical modeling of biological system. I think it had 2,000 hits. I have to say that Perelson and Neumann, at that time and even now, they're not using nonlinear mixed effect models. They're using individual regression and more. On the statistical part, it's not very advanced, but on the modeling part, it's very advanced. So what is this model doing? And I'm trying to show it to you, although it's not optimal design. I thought it was interesting. First, we have to understand how drugs work. This is supposed to be a CD4 cells, and this is supposed to be an HIV virus. The way HIV infection works, it enters the CD4 cells, it liberates its RNA, and then the RNA is transformed to DNA, which is incorporated in the nucleus of the CD4, and the CD4 then makes new RNA and linked with other things that make new viruses. This is a small summary, I'm sorry, but... And presently we have 4 kinds of drugs acting to stop that. Fusion and entry inhibitors stopping the entry of the virus in the CD4 cells, but in my study I don't have these drugs which are new. Reverse transcriptase inhibitor like AZT, and we have them, which block the transformation of RNA to DNA before incorporation of the nucleus. So we have 2 of these drugs. We have integrase inhibitor, I don't have them in my study. And then we have protease inhibitor, which blocked the production of mature HIV virus. So we want to explain that in differential equation. So what are we going to do? First, in absence of any HIV infection, CD4 cells or T cells are produced and eliminated in our body. So it's easy to write an equation for that. So I will call T the CD4, like T cells, and non-infected T cells, that's their differential equation in human being. What happens if you have an HIV infection? You have infectious virus, and then what happens is that you have part of this non-infected CD4 that become either latent infected, so they're latent, or active infected, so they're producing new viruses. And all these cells have natural death. So this is a dynamic model of HIV infection. In absence of treatment, we have new parameters, and you can write that as a differential equation, where you have now three kind of CD4 cells, non-infected, latent, and active, and the virus, infected virus, and new parameters. Now we can add the effect of treatment. First, the effect of reverse transcriptase inhibitors. As I've shown you, it blocks the creation of DNA, so it blocks the creation of latent infected or active infected cells. And the way we do that, we assume that only a proportion of the CD4 will be latent infected or active infected. And this is a new parameter, eta RTI, which is how much we block. If eta RTI is 0, there is no activity of the treatment. If eta RTI is 1, the treatment will be perfect. And we know that they're not perfect, that's why we need combination of drugs, but it's very important to estimate this eta RTI, what will be the efficacy of the treatment. We can have also protease inhibitor, which prevents the formation of infectious virus. The way it's done is that it's creating some of the virus are indeed infectious, but some of the virus are wrong, let's say, and they're non-infectious. And eta pi, again, it's explaining the proportion or the activity of the drug. If eta pi is 0, we all have infectious virus. If eta pi is 1, we'll have only non-infectious virus. So, and now, we can have, because we have a tri-therapy, action of the two of them. And this is explained by this model, where we have now 3 differential equations for the T cells, and 2 differential equations for the virus, and 11 parameters here, and this is the activity of the drugs. So, we did implement these HIV dynamic models. All the reds are the parameters. There are 11 parameters here. But what we do observe is not all of these. We observe the sum of the viral load, so infectious and non-infectious. This is what it's observed. And we have a total CD4 count, which is the sum of the 3. And we were indeed able to estimate all these parameters, most of these parameters, using the SIAM algorithm in monoliths. We had to fix some of the parameters to some literature data. We had to assume that some parameters have no random effects, but then we were able to estimate most parameters with quite a good precision. Yes, thank you. And we found out that indeed the efficacy of, we find that the activity of RTI is 90%, PI is 99%, which is quite good, but nelfinavir was significantly less active than the other drugs. This is an example of individual fitting of this model, showing patients where the drug works and patients where the drug doesn't work. This is the predictive check, 90% confidence interval showing much less response to nelfinavir than to the 2 other drugs. Let's go to optimal design. So we wanted to evaluate first an initial design with 115 patients that would receive only the good drugs. We assume here that viral load and CD4 will be measured in the same sampling time, which is what's usually done, and that we will have 9 sampling times, which is exactly the sampling time of the effect. Then we wanted to try to find optimal design with 6 sampling times only in each patient, similar for those 2. Either a design with the same total number of measurements, either a design with the same number of patients, or either a design with the same information. And these are the parameters that we used. This is the graph of the initial design. This is how we implemented the model in PFIM. So you have to write your differential equations here and give your initial conditions.
Friends,
Yes.
you do not. Oh,
Yes, yes.
you do not want us to read your text.
No, I just want, no, of course I don't want you to, I want you to trust me that I did implement correctly my differential equation. It's just to show you that it's R and you could do it more or less by yourself. No, I don't want you to read it. I just, no, okay, I could have skipped that slide. Just, okay, so the initial design are 9 sampling times here, and the optimal design we find at 6 sampling times, and we find here, which is perhaps straightforward, that the 3 points were during the first curve and the 3 points were during the second curve. Here are the results comparing all these designs. So we find out that a design with 6 sampling size instead of 9 should be performed in more patients, but has a greater efficiency than the initial design. If you go down for a design with the same number of patients, I'm sorry, here, you have a less efficiency, but you have much less sample. And if you want here to look at a design with the same number of, with the same efficiency, you'll have more patients, but less samples. And if you look at the predicted standard errors for all of these designs, the initial and the optimal design, you see that going from 9 samples per patient to 6 samples per patient, optimal, you have very close standard error, here for all the fixed effects, and here for all the variance components, the interpatient variability and the residual error. Then, we wanted to look at the power to detect a decrease in efficacy by nelfinavir. So we assume that 30% of the patients will receive nelfinavir and 70% will receive the others. We wanted to evaluate the initial design to predict the power and the number of subjects needed, and an optimal design where here we did just the optimality, we didn't do power analysis, power optimality, but we assume that we have an additional effect on eta pi. So I think I'm going to skip how we did it because of time, but it's, we just added an effect of covariates and additional fixed effects, which are the effect of covariates, and we evaluated the expected matrix assuming the distribution. And we evaluated the power of the test. This is the kind of output you have. So let's go to the results. We find out that the optimal sampling time was the same with and without the covariate effect, which was not a constraint we imposed. And we find out that indeed the initial design has a power of 78%, so that if you want 80% power, you need 120 patients. But if you use the optimal design, then you will need 131 subjects, but in total we have much less sample to get the same power of 80%. Okay, to conclude, I have hope I've shown you that we have performed, and we, I mean, all the group of people working on design in pharmacometrics and nonlinear mixed effect models, several recent statistical extension for complex multi-responses models incorporating ODE. We allow to have different optimal cycling times across responses. This is what I've shown in my first example. We can predict the power of the Val test and the number of subjects needed. I didn't show, but we can incorporate within subject variability for crossover trials and cost functions. There are now several software tools available, most of them free, PFIM in R, the other in MATLAB, and there is no excuses for pharmaceutical company or pharmacometrician to use these design tools to define what are the good design, but also to anticipate what are the very bad design. As I said, PFIM relies on a priori information both on models and parameters, so it's doing presently only local planification. So I think it's very important to study sensitivity to the population parameters and the models, to define compromise design, to look at sampling windows, and Steve Duffel is going to give a talk about sampling windows, or use robust approach. We're working on new developments that we would like to implement in PFIM. Design with cost function is only available in a working version, it's not available on the web. Design for model with non-diagonal variance matrix, and you can see the poster of Cyril Dumont here, he's one of my PhD students about that. design for estimation of individual parameters, and design taking into account data below limit of quantification. Perhaps one of the limitations of all the work I've presented here is the evaluation of the Fisher matrix, which was F4 approximation. And we know that there are people working in other approximations. However, in lots of simulation, we have seen that we have quite good results. Even in another paper where we use HCV model in StatInMed, it was working well. But we have lots of discussion about this approximation, and we'll have that on Friday. Or we can try to go for exact evaluation. We're working on Gaussian quadrature, and you can see another poster of Tutui and Guillen. She's another PhD student, and she'll have a poster this afternoon. But we can also discuss about stochastic approaches. And with that, I thank you for your attention.
Questions or comments?
Stupid question. So you say PFM needs the prior information. That's what comes from that other program,
Yes.
and I forgot its name. So.
Yes. So you're using it if you want to design a second study after knowing something about the drug. Yes.
This is what's called locally optimal design.
Yes. Yes.
I think your criterion was based on the optimality.
Yes. Yes.
We're following on from the question for the first example where you said you were not interested in the parameter Ka, that you could have considered DA optimal.
Yes.
criterion.
I could have done that. Yes. No, I agree with you in that usually physicians are not so much interested in K. Yes, that's a good point. Or assume that K is known. I could have assumed that K is already known and it's not a parameter of my model.
So why are you not interested in K?
Well, no, yeah. Well, usually it's you're not interested. It depends. It's not a parameter that really tell you a lot about how the drug acts. You know, for example, the mean concentration that you have in your body, it's independent of Ka. But if you really want to have no a priori knowledge, you will need to estimate Ka. It's more pharmacology debate.
And it's highly variable. Yeah, it depends.
But it's not because it's variable that you don't have to estimate it. That's just saying I don't.
It's highly variable and unimportant in the long run.
I comment about K. I say still because I think it's the only found D here. No, we have two of them. Three.
Another naive question. What do you really want to do? You want to predict, like, for future patients, their possible cause, right? Shouldn't that feature then as your criterion somehow? Like the d-optimality, I assume, is just a proxy for scientific learning in some sense.
Yes,
You just had a discussion about you really care for the parameters.
Yes.
You really care for future patients, right?
Yes, I agree with you. That's what we want to do here. I say, knowing the models, now I have new patients. What are the optimal sampling time for these new patients? But it's not at all what I've presented here. Here I was discussing, if I have to do a new trial with these drugs, what will be, and if I want less sample per patient, where to put the sampling times. So it's not exactly the same question. But I agree with you, your question is very important. It's not following a cohort of patients, it's following one patient. And then you have to use different criteria and different Fisher matrix. Because it's not the same Fisher matrix, and I've done that. It's not the same Fisher matrix for fitting a nonlinear mixed effect models in a cohort of patients than for doing Bayesian estimation of the individual parameters of one patient. And I think it's what you said. It's predict or estimate. It's different. And I agree with you. We should do that also for prediction of new patients. And we'll have different optimal design.
My question, if you tested on the presence of random effects.
Yes.
I mean, you introduce individual specific parameters, but do you have evidence that these variances are greater than zero?
First, I have some evidence when you look at the data that there is indeed interpatient variability, because when you look at the response to the drug, you could see that.
Did you use some statistical tests?
In the biometrics paper about which parameters are fixed and which parameters, I think we only use the Bayesian information criteria. At the beginning, we assume random effects on all parameters, And we find out that some of them are quite small or not very well estimated because there's 11 parameters.
That was a heuristic approach, or you use a rigorous statistical tests?
Also, it appears in January. We submitted like 2 years ago. I have to look at my computer. I'll tell you tomorrow. I think we only use the Bayesian information
My
criteria.
point is that
Not us.
many people don't do that.
No, so I think we did.
And it leads to overspecification of your model. So your model becomes very complicated, and maybe simpler model can do the same job.
Okay. Yes. That's a good point. Yes.
Any other questions?
I just want to echo what seems to be an emergent comment that, and this also reflects Don Ubisaker's constant comment that de-optimality is way, way overused. And in practice, really what you want to do is prediction. But people use de-optimality largely for convenience, and it's the simplest thing to do. And there are also lots of examples where if you take out a parameter that you are really not interested in, you can do really better than focusing on. So that talks about multiple objective where you target specific parameters of interest.
Yes.
So I think prediction, and Rainer talks also
Yes.
suggests that designs can be quite different.
Yes.
If your ultimate motive is to predict,
Yes.
we should be really focusing on predictive design.
I agree with you. I agree. And I've listened to your talk, and I really asked you slides about multiple objective function. Yes, I agree with you. It's really, yes.
It is important to learn about the function before you predict.
Yes.
The
Yes.
function that you predict.
And beside all, actually, Jack Kiefer proved that the optimality very much solve in minimax manner the problem of prediction. So, you see, Jack.
Well, in a very
sure
restricted
that,
setting.
Illustrator knows it quite well.
Yeah, right.
So don't, you see, the optimality has some nice mathematical properties. That's why people use it. And beside of it sounds great.
I want to clarify, were you alluding to like de-optimal design maximizes the power, or is it good for testing? Was that what you were alluding to? Like,
Yeah, I am alluding that there is so-called Kiefer equivalent theorem.
yeah.
So what this Kiefer equivalent theorem in the simplest case says is, it says that if you have to minimize the maximum variance of prediction
right.
on your design region, it is, and you want to build optimal design for this so-called minimized design, whatever you can, that this optimal design coincides with the optimal design, period. It's Kiefer-Wolfowitz theorem.
Yeah, but that's under a restricted setting, right? When you're homoscedastic.
Yeah, but and at the same time, even Staden already in '63 knew that to do best prediction, you have to do it at Chebyshev points and all this stuff. So people understood this, but nevertheless, Staden advocated for the optimality.
Thank you, Valerie. The first time you say something nice to me.
This can be generalized.
About the science, I mean.
Homogeneous variance.
But you have heteroscedastic, that equivalence doesn't hold, right? When you have heteroscedastic errors.
No, it's correction, with some correction it holds. It just,
But it's no longer equivalent, the D and the G are no longer equivalent.
yeah, but then it's equivalent when you multiply D by some function. Okay, we can talk about
One more
later.
comment.
Because I have to take a photo now.
Rainer, do you want to?
I just want to comment on that this equivalence does definitely not hold in mixed models.
Yeah,
There are
exactly.
simple examples where E and G optimal fall completely apart.
Yeah, but it depends upon how you formulate equivalent theory, you see, because it depends upon, we can talk, and I will talk about this a little bit tomorrow. So it's close, it's not far.
There are simple models, situations where they are very far apart. Random slopes.
We just have to look at proper equivalent theory.
Maybe proper